First, I would like to thank the organizers of the 23rd International Conference on General Relativity and Gravitation for the opportunity to present results on the possible quantization of stress energy tensor and on Tensor's manifold. The main physical problem is the unification of general relativity and quantum mechanics. To do this, we propose to quantize the general relativity on one hand. On the other hand side, we also need to gravitize the quantum mechanics. Quantizing general relativity means providing the theory with rough space-time at some scale, at relativistic energy scale, providing space-time discretization or quantization, if you like, allow for some measurement uncertainties, and impose some non-commutative relation. This can be achieved if we move from the pseudo-Riemannian manifold to a generalized manifold. With gravitizing quantum mechanics, we mean to provide the theory with a smooth space-time at some energy scale. This takes into account the impact of gravitational field, and also needs to generalize the non-commutativity and take into account relativity principle, isotropy property, and also Lorenz covariance. To achieve this, we propose to use the minimum measurable length, which sets limits on the space continuity, so that at low scale general relativity coordinates shouldn't be arbitrarily smooth. And to summarize this, we mean with quantizing general relativity to allow the theory, the classical general relativity, which is applied at large scale, to have corrections at low scale. And with gravitizing quantum mechanics, we mean to provide the theory with an extension which make it possible, it's valid or applicable at large scale as it is at low scale. We utilize the non-relativistic generalized uncertainty principle. One of its proposal is depicted in this expression, where you have the Heisenberg term, the first term, and you have additional terms. Also, with the uncertainty principle, you have additional to the Heisenberg term, the h bar over t over 2, the half h bar. You have additional quantities, including uncertainties in momentum and expectations value, and so on. This leads to, or this results in, minimum measurable length equals square root of 3 beta 0 multiplied by the Planck length. This means we modify, extend the lower length or the minimum length not to play or not to count just on the Planck length. The parameter beta 0 can be determined from observation, because astrophysical observation, from even from top table laboratory experiments. There is another approach was suggested by Maggiore, motivated by quantum deformation of the Poincare algebra, and this also leads to the minimum measurable length. But this non-relativistic generalized uncertainty principle is not suitable to be applied one-to-one in general relativity. Therefore, there is a need to go to extend this to relativistic version. Why we need this? Because in the non-relativistic three-dimensional GOP has no temporal dimension, and therefore either the commutator nor the uncertainties are not necessarily Lorenz covariant. This also means that the minimum measurable length is frame dependent, and this causes a problem with the linearity of the additional law of momenta. To avoid all this problem, I'm introducing here the Lorenz transformation represented by the unitary operator U, with which we can also we can transfer the coordinate and momentum. With this transformed coordinate and momentum, we can write down here the commutative or non-commutative relation in this form. This version of the non-commutative relation is Lorenz covariant. Again, the non-relativistic QP generalizes the momentum but not the length. Accordingly, the dispersion relation is deformed. This deformation leads to non-linear additional law of momenta. To show that the new proposal solves this problem or doesn't suffer from this problem, I start with the Poincare algebra and with the Lorenz transformation generator mu nu, where m tilde m prime union nu given in this expression. Therefore, this parameter, this operator B covariant mu, B contravariant mu is Casimir operator of the Lorenz algebra and commutes with momentum and B square. Also, this operator commutes with other Casimirs like W mu, which is given in this expression here. This leads to that this operator can be determined as the c to the power 4 m squared, which means square dispersion relation, and therefore fulfills the linearity of additional law of momentum. Third problem is that to assure that the minimum length of the is Lorenz invariant. To show this, I start with the space-time non-commutativity given in the first line, the equation in the first line. Also with the length momentum non-commutativity. This is given in the expression here in the third and in the middle here. Therefore, we can determine the commutative or non-commutative relation of x mu, which given in this expression. This means that the space-time coordinate are likely non-commutative, have some similarities with the Snyder algebra, but are not forming a closed algebra because they are depending on momentum, on the B nu, and also on the generator, Lorenz transformation generator. The relativistic GOP, the relativistic general uncertainty principle, we start with the physical position and momentum, which can be also expressed in their auxiliary form for vector x0 mu, p0 mu, where these vectors can be separated into temporal x00 and p00, and also into the spatial component x0i and p0i, where I runs from 1 to 3 and p and u are 4-dimensional, run from 0 to 3. The parameters x00 and p00 can be determined from the stress energy tensor. The auxiliary for vectors are canonically conjugate variables so that we get this commutation relation. This is the relativistic generalized uncertainty principle, where we have here the Heisenberg term and additional two terms here. Here, eta mu nu is the metric tensor, is a Minkowski metric tensor, or metric tensor, or metric in the Minkowski space. From the Robertson uncertainty principle, which allows for, which follows from the Schrödinger uncertainty one, we can relate the uncertainty to the commutation or non-commutation relation. Therefore, the relativistic generalized length momentum uncertainties in curved space-time means we replace eta mu nu by g mu nu is given in this line, in this bottom line here. You have here a second, or you have here a squared equation to be solved, in this inequality to be solved. To have real roots for the uncertainty in momentum, delta p, it requires that the delta x mu fulfills this inequality. This leads to another condition to be fulfilled, which gives us opportunity to determine the minimum measurable length, so that the delta x min mu greater than or equal to plus or minus the square root of minus g mu nu multiplied by h bar multiplied by square root of beta. The square root of beta can be replaced by its physical component, so that we can relate the delta x min to the Planck length LP. This result is very interesting, especially that it contains, it has also the term or the coefficient square root of minus determinant G, determinant of the metric tensor, because in general relativity there is no physical dimension assigned to the coordinates. The coordinates in general relativity are fundamentally arbitrary. To assure that they have some physical meaning, or to assure that the coordinates are invariant under transformation, we use the Jacobian determinant, which can be related, which is to be related to the square root of minus det G, depending on with some sign. What we have here is showing that our minimum length is frame independent or Lorenz invariant. And now we can determine the uncertainties. We start with the length. X min we can express in x0 mu. X mu can be expressed in x0 mu subtracted delta x min, so that the uncertainty delta x mu equals delta x0 mu, and also we subtract the value of the delta x min. Same can be done for the momentum, which can, the momentum can be deduced from the solution of roots of this expression, and accordingly suggests that delta, the uncertainty in mu nu is limited to, is greater than this one and less than this quantity. For simplicity, we can assume that the squared delta x min, which is small, when squared, this quantity becomes much more smaller. Then we can neglect this term, and accordingly, delta p is less than or equal to 2 divided by h bar beta, or are multiplied by delta x mu. This means the uncertainty in momentum depends on the uncertainty in coordinates. This is not just a non-commutative relation, but also makes non-coherent measurements. I mean, if you measure momentum, you disturb the coordinate, and vice versa. If you measure the coordinate, you disturb the momentum. This makes your measurement in general relativity no longer coherent and no longer precise as they are in the current version of the theory. These results were correct, and we think they are correct, at least at the relativistic energy scale. Then we can conclude that the space-time is neither smooth nor continuous. There is some inaccessible space-time element whose volume characterized by this delta x min. Not only coordinates and momentum are certain, as we have shown, but also other physical quantities should have some non-commutative relation as well. Due to uncertainties, events likely happen in jumps with non-deterministic outcomes, and as I discussed, the measurements are likely neither precise nor non-coherent. To generalize the metric tensor, we need to generalize, or we think we have to generalize the Riemannian manifold. Actually, a Riemannian manifold is a special case of another generalized manifold, which is a Fennesland manifold. Just a short review about the Riemann geometry, which depends on the manifold M and the metric tensor G. so that at the point x, as depicted in this picture, we can determine the metric tensor as g mu nu dx mu tensor product dx nu, and also we can determine the length of the curve C, which can be estimated from the integral over the curve C, or limited integral over the path S from S1 to S2. In the second option, we have x dot, which is the rate of x with respect to the S. In Fenster manifold, Fenster manifold depends on the manifold M and on F, where F is called the Fenster structure, which depends on the coordinate x and the tangent vector x dot. So that we can also determine the metric tensor at the point x given with this f function or f structure. Here I'm just flashing or displaying properties of this Fenster structure. F is positive for non-vanishing x dot on the tangent bundle T mu, and F is homogeneous of degree 1 in x dot. Therefore, on the tangent bundle at the local coordinate x comma x dot, the Fenster structure can be shows this property, which means when we have the property the coordinate x comma lambda x dot, then it's just lambda. We can subtract lambda, and what we obtain is lambda multiplied by the f itself. Another property is that the ratio of lengths of any two collinear vectors doesn't include metric tensor. And we use both properties here to determine the metric tensor in Fenster manifold and relate this to its counterpart or its equivalent part on Riemann manifold. This is the idea here. In Fenster manifold, we have the special case, the structure F, given in this expression. This F distinguishes Fenster from Riemann geometry. We mean that this function or the structure F is relaxed, or this relation is relaxed in Fenster manifold or geometry, but are restricted on Riemann manifold. Therefore, the length of a curve C can be given by the integral of this structure F. As we have started with the minimum measurable length, if delta min mu sets limitation on space and momentum coordinates in general relativity and determines the uncertainty, and also dictates how the measurement can be done, then why not we can deal with this delta min, or we can introduce delta min mu to the Fenster manifold. Under the condition that this delta x min mu should be positive. This allows us to determine the metric tensor on the tangent bundle on the Fenster manifold, GAB, capital A, capital B, equal G mu nu tensor product G mu nu, where each G mu nu is homogeneous of degree 0 in x dot, and A and B run from 0 to 7. They are eight-dimensional quantity. The GAB on Tm can be determined from the Hessian in the x comma x dot coordinate by this expression. When we do this, then we can relate the G mu nu on Riemann manifold with the GAB on Fenster manifold with this expression. What we need is to determine the partial derivatives here, partial XA by partial zeta alpha, partial XB by partial zeta beta. When we do this, we obtain this expression for the generalized or modified or quantized metric tensor on a Riemann manifold related to its version, its counterpart on tensor manifold. To summarize, for quadratic f, g mu nu reduces to g mu at the point x living on the Riemann manifold M, while on Tm, the bundled on the Tensor manifold, the coordinates are 8-dimensional, where xa equals to, or is the xa comma delta x min x dot a. This allows us to determine the line element on Tm, the tangent bundle, and also the line element on M, on the Riemann manifold. As we have restricted ourselves to the quadratic f, which is homogeneous, this allows to that the ratios of lenses of any two collinear vector are not depending on the metric. We can equate the line elements on Tm and with that on M. This allows us to get this expression for the g mu nu. Here tilde, because we think this is quantized or this is extended. It's equals to the standard one, g mu nu, plus g mu nu multiplied by tau and multiplied by x double dot squared. Tau is a quantity which includes all quantum components of this extension. The quantization of this perturbation of this additional term is possible through coordinate independent discretization given in this expression, and also from possible from the second order derivatives of the coordinate x double dot squared. X double dot squared could be treated as a space like for acceleration or local geodesic equation. To account for the consequences of the existing of delta x min mu, we went to the tangent bundle T mu nu and assumed quadratic Fensler structure, from which we have obtained that the g mu nu reduces to the usual g mu nu at the point x, which is living on the Riemann manifold. Now we can determine the stress energy tensor. We are equipped with all facilities to do this. We start with the full action in curved space, which consists of the Einstein-Hilbert action with and a non-gravitational part of the Lagrangian density in matter. The physical quantities, including the Hilbert space. The Hilbert stress energy tensor can be determined from demanding vanishing variation. I mean, we variate this action with respect to the inverse metric tensor G contravariant mu nu. This allows us to obtain T mu nu, and with the modified G mu nu, with the quantized G mu nu, we can also G mu covariant. We can also determine the quantized G mu nu contravariant and its variation given by this bottom line. When we substitute with delta G mu nu contravariant in the stress energy tensor, we obtain this one. What we are left with is an expression for the Lagrangian, for the matter Lagrangian. This is a generic expression for the Lagrangian density, and from we can here discuss two cases: the electromagnetic field in curved space. This can be expressed using the Faraday tensors and so on. What we obtained is that the modified LEM, electromagnetic, equals the unmodified or the classical LEM multiplied by a quantity which is includes the quantum induced corrections. This means the quantum-induced corrections are linearly factorized to the classical Lagrangian density. Also, if we go to, or if you study the Klein-Jordan field, means the scalar field, we can also quantize this, and this gives us this results in also corrections to be added to the standard or to the classical ones. Here I'm circling the contributions coming from the quantum correction. Now we can plug everything into the T mu nu, the modified T mu nu or the quantized T mu nu. What we obtain here is for electromagnetic Lagrangian, we have here the quantities, the quantized quantities or terms circled by red lines here or red curves here. This shows that the quantum-induced correction are linearly factorized to the classical T mu nu. Also, this means if you send everything here, send the corrections to 0, you assume vanishing corrections, what you obtain is the classical T mu nu. It means the T delta mu nu equals T mu nu. The next step is to determine or to have the covariant derivative of the stress energy tensor for this electromagnetic Lagrangian given by this expression here. Here, just a short discussion that the unquantized, if we remove the quantization, the unquantized stress energy tensor means vanishing beta 0 or vanishing x double dot square. The covariant derivative vanishes as well. For the quantized version of the stress energy tensor, where beta or x double dot are finite, if we are in vacuum space-time, also the covariant derivative vanishes. But if we are not in a vacuum, if we have finite f mu nu, then the covariant derivative is not vanishing. It's divergent. Thus, in this case, the Lagrangian density should be equal to some charged particle as a source of the inhomogeneous Maxwell equation, so that the covariant derivative of the T mu nu, the electromagnetic version, plus T mu nu, the particle from the particle field, this one is vanishing. For the case of the scalar Lagrangian, again, we obtained quantized version for the stress energy tensor. And here just I'm circling the contributions from the quantum corrections. Again, these contributions are linearly factorized to the classical T mu nu. If we send everything to vanishing values, what we left with is a classical component. Here the covariant derivative vanishes, and we conclude that the stress energy tensor is not explicitly depending on the coordinate. I mean, it's locally conserved. Now, I summarize. I have introduced the relativistic G mu nu. I started with the coordinate and with momentum component, which could be separated into temporal and spatial component. I have discussed the non-commutative relation and its properties, that it is Lorenz covariant, it assures for linearity of addition law of momenta, and assures that the minimum length is Lorenz invariant, and also from the uncertainty principle, which also modifies the Heisenberg one, we could determine the delta x min, the minimum measurable length, and we found that it depends, or it is related, or it is generally have this square root of minus g mu nu, assuring that this quantity, this result has a physical meaning and it is frame independent. It is also related to the Planck length, from which we can determine the uncertainty and the coordinate delta x mu, and we find this is connected by the delta x min. For the momentum, we have done the same and obtained uncertainties for the momentum. And we found that this depends linearly, strongly depends on the uncertainty on coordinates. This means that the measurement of one quantity influences the measurement of the another one. This also means that the measurements are coherent. And we modified also the metric tensor, which is a key modification we have done when we went to the Fenster manifold and determined the line element on the tangent bundle, and also the line element on Riemann manifold. By equating them and do some algebra, we obtain that the G mu nu, the tilde, the quantized one, equals to the classical one, G mu nu plus correction plus perturbation or plus quantization or quantized terms. The quantized induced correction are linearly added, so that when send this correction to 0, we just obtain the generativity metric tensor. Last results we have obtained is the stress energy tensor, quantized version, and we have seen that the quantized or the quantum induced correction are linearly factorized to the classical T mu nu, so that vanishing correction retrieves the G mu nu, the stress energy tensor, the classical one, the generativity one. Thank you very much.